Hi dear students, this is Fybsc, Assistant Professor, Department of Chemistry, Gokhale Education Society's Arts, Commerce and Science College, Jawar, District Palghar. Dear friends, in the last part of the video, we discussed about the various physical properties of liquid state, particularly surface tension and viscosity. At the same time, we also discuss about how this viscosity and surface tension can be determined experimentally with the help of different techniques. And we discussed about the various types of viscosities like relative viscosity, specific viscosity, intrinsic viscosity, and how this viscosity, particularly intrinsic viscosity, is used to determine the molecular mass of the given solid according to Mark-Having equation. Dear friends, based upon the same, today in this part of the video we are going to talk about the determination of viscosity by a viscometer, which is called as the Ostwald viscometer. So in this method, the measurement of viscosity of liquid is based upon the Poiseuille's equation, and this Poiseuille's equation gives a rate of flow of liquid under a definite pressure through the capillary tube, and it is convenient to determine the relative viscosity of liquid rather than the exact viscosity. And for that purpose, we are going to use a water to determine the relative viscosity of the given solution. Suppose here neta 1 be the viscosity, of the given liquid having the flow time T1 and pressure P1, and neta 2 is the viscosity of another liquid or whose viscosity is to be determined having the flow time T2 and the pressure will be P2. So according to the Poiseuille equation already we discussed in the last part, this viscosity or the coefficient of viscosity is related to flow time and the pressure, that is driving pressure. And this equation can be written for the two liquid, one is the reference liquid and another one is the given liquid. So definitely we are getting this equation for the first liquid in neta 1 is equal to pi r raised to 4 into T1 into P1 divided by 8 into VL. I hope you can understand about this. R is the radius of the capillary, T1 is the flow time of the given liquid, P1 is the pressure, V is the total volume, and L is the length of the tube. And here for the another liquid, definitely we will write the same equation. Here V, L and R will be same because we are using the same capillary, we are using the same Ostwald viscometer. And if in this way we will divide this equation 1 by means of equation 2, definitely we are getting only this, that is neta 1 upon neta 2 is equal to P1 into T1 divided by P2 into T2. Here the pressures P1 and P2 are proportional to their densities D1 and D2 of the two liquids, and these pressures can be replaced by means of their respective densities D1 and D2, and that's why equation 3 can be written as neta 1 upon neta 2 is equal to D1 into T1 divided by D2 into T2. So from this equation number 4, if D1, D2 and neta 2 are known and flow times T1 and T2 are measured by means of Ostwald viscometer, then the viscosity coefficient of another unknown liquid can be calculated. This is very simple. And what is the procedure here? This is the figure that indicates the Ostwald viscometer. This is the one arm, this is the other arm, and there is one bulb, and definitely this bulb is having the capillary, and there is a two marks, mark A and the mark B, and definitely we are going to record the flow time of liquid from mark A to mark B, and the quantities T1 and T2 are conveniently measured with the help of Ostwald viscometer. The bulb in the wider limb of the tube is first filled with the liquid, and then the liquid is sucked up in the narrow tube or the narrow limb until the liquid level is above the mark A. The liquid is allowed to drain, and the flow time T1 for the liquid to flow through the capillary tube from A to B is measured, and the same procedure is repeated with the reference liquid like water in the same tube, and corresponding flow time is recorded as T2. Hence T1 and T2 are determined, or these are obtained, these are measured with the help of viscometer, viscometer, and the viscosity of the unknown liquid can be determined in this way. Definitely based upon the same, there might be numericals, but these are the types of long question. Dear friends, there is another important property of the liquid that is called a refractive index. Generally, it is observed that when the liquid or the light passes, when the light passes from one medium to another medium, then it shows a change in the direction. Then it shows the change in direction of passing, that we call it as the refraction. So whenever light passes from one medium to another medium, it shows a change in direction called as refraction. And if R is the angle of incidence and R is the angle of refraction, I hope you can understand about the angle of incidence. I will show you later on this here. This is the light. Suppose this is light which is passing from this one medium air to another medium liquid, and it incident at this point. So this angle is called like the angle of incidence. This angle is called like the angle of incident, and this angle by which it get transmitted from this point to this, and this is called as the angle of refraction. So these are the two angles. I is the angle of incidence and R is the angle of refraction. Then the refractive index can be defined. The ratio of sine of the angle of incidence, ratio of sine of the angle of incident to the of angle of refraction is constant, and it is the characteristic of that liquid, and this constant ratio is called as refractive index. So this is simply the ratio of angle of sine of angle of incidence to the sine of angle of refraction is constant, and is called as the refractive index of the liquid. So this is the important thing to define the refractive index. So this is the ratio of sine of angle of incidence to the sine of angle of refraction. The refractive index of the medium can be also defined as the ratio of the velocity of light in vacuum to the velocity of light in the given medium. So this can be also defined in terms of velocity of light also. And the first type of the refractivity is called as specific refractivity, indicated by R. Refractive index of the liquid changes not only with the wavelength of the light but also with temperature. And to eliminate the effect of temperature, Lorentz gives a theoretical equation, that is R equal to n square minus 1 upon n square plus 2 into 1 upon d. Here n is the refractive index, d is the density of the given liquid, and R is called as the constant, that we call it as the specific refractivity of the given liquid. This specific refractivity of the liquid represents the refractive power of 1 gram of the liquid. It's very important. Sometimes question can be asked to you, what the specific refractivity indicates, or what is the significance of specific refractivity. So this specific refractivity of the liquid represents the refractive power of 1 gram of the liquid, and based upon the specific refractivity we are also able to define the molar refractivity. Definitely word itself indicates molar refractivity. So here, in order to compare the refractive powers of different substances, the specific refractivities are multiplied by their respective molecular weights, and the resulting product is called as the molar refractivity. Whenever specific refractivity is multiplied by molecular mass of the given substance, then this is called as molar refractivity. That's why this molar refractivity Rm is given by this equation, that n square minus 1 divided by n square plus 2 into m upon d. The m is the molecular weight and Rm is the molar refractivity. Molar refractivity is the characteristic of given liquid, and it is independent of the temperature. It's very important. It is independent of the temperatures. And unit of molar refractivity is simply given by the decimeter cube per mole or meter cube per mole. And molar refractivity is an additive property. It is not a constitutive property, it is additive property, and it is also found to be constitutive property, as it is influenced by the arrangement of atoms in the molecule. So here, dear friends, I want to correct one thing. So molar refractivity is an partly additive and partly constitutive properties. This is the important. Here there is one numerical based upon the refractive index. Dear friends, the refractive index of carbon tetrachloride is given, and it is 1.4575, and its density is also given 1.598 into 10 raised to 3 kg per meter cube, and calculate the molar refractivity. Here there is one short numerical. that in a molar refractivity is directly given by the equation n square minus 1 divided by n square plus 2 into m upon d. Already we know the values of refractive index, means the n density is also given, and we know the molecular mass of the carbon tetrachloride, that is 154. So definitely in the kg it will be into 10 raised to minus 3. So by putting all this value and by simplification we will get the molar refractivity equal to 26.27 into 10 raised to minus 6 meter cube per mole. How this refractive index is measured, that is also the important. But the measurement of this molar refractivity or this refractive index, the most commonly used instrument for the measurement of refractive index of any liquid is Abbe refractometer. So this is the instrument which is used for the measurement of refractive index of the given liquid, called as Abbe refractometer, which is shown here. That is, this is the Abbe refractometer. I hope you can understand. But measurement of this refractive index is not too much important for you. This is just long and theoretical. So as far from the way of MCQ, this is definitely the value of refractive index depends upon the temperature and the wavelength of the light. Here you have to keep in mind this thing, and definitely, so here this is the important thing that can be considered here, that how this refractive index can be explained. The another part of the study of liquid state is called liquid crystals. Generally we are using this term crystal for the solids, but here we are going to talk about the liquid present in the crystalline form, that is crystal, liquid crystal, a substance which flows like a liquid. The substance which flows like a liquid but has some degree of ordering, the arrangement of its molecules is called like the liquid crystal. So it shows the properties of solid also, and it shows the property of liquid also. So it flows like a liquid, but it shows the degree of ordering, the arrangement, or there is arrangement of molecules or the atoms in a structure, and it's called as the liquid crystal. So certain solids when heated undergo two sharp phase transformations. At first stage they fuse sharply and gives turbid liquids, and then again fused sharply at higher temperature to form the clear liquids, and these changes can be reversed by cooling also. Initially it becomes turbid and then it becomes the clear liquid on heating, and again if we decrease the temperature, this clear liquid will be converted to turbid liquid, and this turbid liquid will be converted into solid again. So this is the important case. These turbid liquids, so dear friends, here you can see solid state can be converted into liquid crystals, and this liquid crystal can be converted into later on clear liquid, that we call it as the liquid state. So this is the turbid liquid. That state is called as the liquid crystal, and if we will decrease the temperature of the liquid state, then it will be converted to turbid liquid, that we call it as the liquid crystal, and again decreasing the temperature, this liquid crystal will be converted into solid state. So here you can say that this liquid crystal is the intermediate stage of solid state and the liquid state. So this is very important to define the liquid crystal. The first temperature at which solid changes into turbid liquid, means this temperature is known as the transition temperature or the transition point, and the second temperature when turbid liquid becomes clear liquid is called as the melting point. So dear friends, here you can consider this liquid crystal is the early condition of the melting of the liquid or the melting point. So this is important in the discussion liquid crystal. This classification, so the classification of this thermotropic liquid crystal can be classified as Spectic liquid crystal, Pneumatic liquid crystal, and the Cholesteric liquid crystal. If we will talk about all these types of liquid crystal one by one in detail, here in the discussion of this Spectic liquid crystal. So this Spectic liquid crystals are the liquid crystal flows in the layers in different planes. So this liquid crystal flows in a layers in different planes, and the sheets gliding one over the other. Each layer will have a different velocity, Again, the Spectic liquid crystals have a non-Newtonian motion when compared with the true liquid, which are having complete the true Newtonian motion. On clean surface, they form the terrace and the strata, while the molecules are oriented in well-defined planes, but there is no periodicity within the planes. Again, the Spectic phase is more solid-like and obtained at more lower temperature. These liquid crystal lattice exist but in a distorted form. They also use extra diffraction pattern but only in one direction, and they have a complex internal structure, fan like appearance, and not affected by the magnetic field. The example of Spectic liquid crystal is ethyl para azoxybenzoate and ethyl para azoxycinnamide, and this is the diagram that indicates the Spectic liquid crystal. Yeah, I hope you can understand this. The second type of this liquid crystal is called as the Pneumatic liquid crystal. They flow more rarely when compared with the Spectic liquid crystal, and this shows a Newtonian motion, and the term viscosity is applicable to them, but their viscosity is low when compared with the true liquids. These pneumatic liquid crystals are less anisotropic as compared to Spectic liquid crystal. They have thread-like structure and are affected by the strong magnetic field, and turbid liquid appearance quite clear. If the magnetic field is removed, the liquid appears turbid again, and in pneumatic liquid the planar structure is lost but orientation is preserved without periodicity. Pneumatic liquid crystals are rod-like structures of organic molecule, and they organize in parallel fashion and used in the LCDs. The example of pneumatic liquid crystal is para-isoxyanisole, para-isoxy that is phenol, and para-isoxycinnamic acid. This is the crystalline orientation, and this is the pneumatic orientation. I hope this is the clear orientation, this is the random orientation. The third type of the liquid crystal is called as a cholesteric liquid crystal. Some compound which are optically active shows similar characteristics of pneumatic liquid crystals, but shows a strong colored effect in polarized light, and this indicates that they have layered structure like Spectic liquid crystal, but differ from Spectic liquid crystal in that they have a thick layers. These liquid crystals, that is the cholesteric liquid crystals, have some pneumatic and some Spectic characteristic and are called as the cholesteric liquid crystal. So this cholesteric liquid crystal shows the properties of that is pneumatic as well as Spectic liquid crystals, and they have high non-Newtonian flow properties when compared with the pneumatic liquid phase or the liquid crystal. There are some applications of liquid crystals, dear friends. One of the application is these liquid crystals are having several applications. Out of these, the first is called as they are used in the number displays. Again, when a layer of pneumatic liquid crystal is placed between the two electrodes and the electric field is applied, the polar molecules are pulled out of the alignment, which causes the crystal to be opaque, and the transparency returns when electrical signal is removed. This property is used in the number displays. These are also used in monitoring body temperature, and these are used for detecting the tumors in the body by using the method called as thermography, and these are also used in commercial lubricants also. So dear friends, these are some important applications of liquid crystals which are used in the day-to-day life for commercial purposes also. So here in this way we try to discuss that is all aspects of these liquid crystals with their classification, with their definition as well as properties and their applications also. So dear friends, in this way we have completed this liquid crystal, and we will discuss about the new topic in the next part of the video called as stereochemistry. So dear friends, we will resume again in the next part of the video to discuss about the stereochemistry of organic compounds particularly. So thank you very much.